Yeah, hello, I'm John Passalacqua. I'm the CEO of First Phosphate Corp in Quebec, Canada. And today I'll be speaking to you about the role of phosphates in the LFP battery supply chain. So, first off, we should start and we should know what is the LFP battery. So LFP batteries are a form of lithium iron phosphate battery. And they are similar to other lithium ion batteries, which are usually made of nickel, manganese, and cobalt. These batteries are just very popular now because they have the advantage of being non-toxic. They have superior fire safety, longer life, and lower cost. So as you can see, all the vehicle manufacturers around North America, even Europe and Asia, have now started to move part or all of their production to LFP battery. What's really interesting is Tesla, which is considered to be one of the leaders out there. They have now confirmed that almost half of their vehicles are using lithium iron phosphate batteries. And that's a real big wake-up call for our industry, and something that we have to really keep some, very close focus on, because Tesla's used this to then decrease the cost of their vehicles, and now the rest of the majors have to follow behind them. And if you see here, Elon Musk is saying that the majority of the heavy lifting for electrification will be done by iron-based cells. And also we have Jim Farley being quoted, CEO of Ford Motor Company, saying that by 2030 to 2035, lithium iron phosphate batteries will dominate. Here are some of the culprits that we can see on the streets, mostly North America, but you can see them around Europe. You can see them in Asia as well. Most of these are Tesla models. Some of them are Rivian models. Some of them are Ford, the Mustang, and then there's some other, freaky new concepts, especially in the light trucks and consumer transportation that are being projected by Tesla. What is going on with LFP battery? I think this is a really key focus for us. Is that, this is really the battery of mass market adoption. And that's a really big thing. Like, just think about what that means. That, this could be the battery that finally makes the electric vehicle, the new standard, something that starts to really compete with fossil fuel cars, and that really gets the quotas up there that the governments want in terms of electrification. Again, they're non-toxic, they have superior fire safety, but, most importantly here, right, their costs, the cost of the LFP cathode active material right here is much less, 50 to 66% cheaper than the cost of nickel, manganese, and cobalt materials. So that's what's really driving the mass adoption. But, it's not only small vehicles, it's also commercial transportation. If you look in Asia, for instance, in China, a lot of the buses and commercial vehicles are now on LFP battery. But it's also the large-scale energy storage. That's that precious electricity that's coming from solar farms, wind farms, and hydroelectric dams. It needs to be stored because it's precious, it's green. So LFP battery is really one of the most propitious technologies for that kind of storage. So now when we look at some of the statistics out there, what I was just talking about is large-scale energy storage could be up to 60% of the use of LFP. And here we have, electric vehicles, and here we have commercial vehicles, and we have other applications as well. Telecom's a big one, 5G towers. So, it's quite broad-based LFP, and that's the good part about it, is that it's not just the one-trick pony. You can see it in a lot of different applications. We believe that, there'll be no shortage of demand for LFP battery and LFP cathode active material. That's the powder that goes into the batteries. The real limitation will be the supply of purified phosphoric acid, which really touches our industry, and which I'll talk about shortly. These batteries, as you can see, LFP batteries, they were projected to be 50% of the battery chemistries by 2030, but it looks like that's already happened here in 2023 to 2024. So they could go much, much higher. Right now, what's happening with these batteries is that 90% of these batteries are produced mostly in China and a little bit more in Asia. So it's really important for the other blocks, such as North America and Europe, to onshore the production of LFP cathode active material. So look for that as a real strong trend, especially with the Inflation Reduction Act in North America, that is. Now, I guess what's important to our industry is, how do we define, phosphate for the LFP battery? Well, obviously it starts with, purified phosphoric acid. And then you start hearing the term now LFP grade phosphoric acid. What is the criteria for it? Everyone's going to think, well, really technical criteria. It is, but it's not. It's also very social criteria, and I'm going to explain that here very clearly. So the specifications for LFP grade phosphoric acid is really food grade phosphoric acid. That's where you start. But then I think for the most part, you need to really look at taking out most of the other concentrations of sulfur and other metallic elements, obviously, because they affect conductivity. So you're starting with food grade phosphoric acid, and then you're going a little bit further. But what's most important is, many of these, what they call ESG, environmental, social, and governance considerations. Electrification is being carried out to save the planet. So the process that we use to make the batteries and the phosphate and the lithium and the iron that goes into making these batteries, that has to be ultra clean as well, because people are going to start looking at our supply chains to make sure that, we are truly, in sync with, the goals of electrification, which is to clean up the planet. So very important as well is these soft considerations such as, traceable, ethical source, consistent, secure, high quality supply. All that's going to be looked at when you make your purified phosphoric acid for LFP battery. And the key feature is really to guarantee a proper life cycle assessment, right? The low carbon footprint and the less pollution possible. Also there's local sourcing requirements that are coming into place as well, such as the U.S. Inflation Reduction Act, and other countries are beginning to follow as well. Now, how do we produce LFP grade phosphoric acid? Well, it's going to be, with those criteria that we just mentioned. In order to eliminate pollution, you have to start with the cleanest possible ore. Igneous rock is preferable, that being, rock that comes from phosphate rock that comes from volcanic activity that has, less gypsum to manage, less radioactivity to manage. So that's why we feel igneous rock is really the most suitable for LFP grade phosphoric acid. And also in the beneficiation process, we have to move to a solventless extraction, low sulfur, and a circular process where we consider all the secondary elements, and then we're able to fully recycle everything that we produce, whether the byproducts or the main PPA. The MGA production process will be a wet route with full recycling of phosphogypsum. We believe that the thermal process of making a purified phosphoric acid starts to become incompatible in North America and in Europe, and will eventually be penalized by the European border carbon tax. So we do believe that the wet process is the way to go. When we look at the different methods of producing purified phosphoric acid, which I'm sure everybody is familiar with, we have the thermal process that emits a lot of pollution, which is not really practiced, outside of China. We've got also the wet process in the rest of the world. So we have the wet process on sedimentary rock, and then we have the wet process on igneous rock. What we like a lot about the wet process on igneous rock is that the gypsum is fully recyclable. It can be made into plaster, wallboard, or it can be used in cement, or it can be used in agriculture. And also using this process, we create a large amount of purified phosphoric acid. 90% of igneous rock generally can be converted into purified phosphoric acid, and only a small amount remains back in a merchant-grade fertilizer-based stream. When you're processing sedimentary rock, it seems to be the opposite. You get a smaller amount of purified phosphoric acid and a larger amount of MGA, which goes for fertilizer. And then, of course, we're also left with the gypsum slag piles, which we all know the issues around that. So really, the process to really change what's going on, perhaps in some areas of Asia, and to make a lot of purified phosphoric acid seems to be the wet process with igneous rock. And that's what we're focusing on at First Phosphate, which is my company. So now, how do we get from LFP grade PPA to LFP cathode active material production? Well, we're kind of lucky because all the patents that were in place until about 2023 are almost all completely finished. So anybody entering the field, does not have to pay any patent royalties. So that's great. But very important in making LFP cathode active material is green power. Green power is fundamental to making LFP cathode active material. So having a facility that's very close to hydroelectric or wind or solar electricity, that's important because that goes into your life cycle assessment, which determines your carbon footprint when you're making the LFP cathode active material. My company, First Phosphate, is found will have its LFP cathode active material facilities most likely in Quebec, together with partners. We have green energy in that area of the world, and that was very important for us, a very important consideration. Then when you're actually making the LFP cathode active material, there's a traditional, what they call the solid state or precursors method of making it. And this is usually motivated by logistical constraints, right? It involves a series of crystallizations in order to get to the LFP. But the newer methods of making LFP are a hydrothermal method, where it's more of a wet method. And it assumes in situ wet materials, which becomes logistically a little bit more challenging. And that's what we're bringing together at First Phosphate, is all the in situ wet materials, hopefully at the port of Saguenay in Quebec, to be able to use some of these more modern hydrothermal methods of making LFP, which will give us, a better synthesis, which will lead to, better LFP in the end that can meet, certain challenges that are, maybe particular to North America that aren't in other parts of the world. So look for the hydrothermal as being, the future method, but the precursors method being a great method nonetheless. So now we say, what does it take in terms of making an LFP battery? How much phosphate goes into it? Well, about 28% of the input into a LFP battery is purified phosphoric acid. I caution, like I said, there's many different ways of making it. There's a hydrothermal method, there's a solid state method, there's what people refer to as a carbothermal method. And then within those methods, everyone has their own, proprietary techniques. But, generally, we can say that about 28% is, purified phosphoric acid, H3PO4 at 85%. Then you'll have about, 62%, which will be an iron source, which is generally iron sulfate. There are some out there that are starting to use iron powders to do that as well. And then, of course, you have the lithium. The lithium is about 10%. What's nice about these batteries is the content of lithium is about a third less than it would be in a nickel, manganese, and cobalt battery. And that's where a big expense is, obviously, in the lithium. So there's a bit of savings there. And then once the chemical reaction takes place, this is kind of what it looks like. There's more phosphate in the end, but that's because the water has been stripped out of these other two elements. Okay, so this is just to give you an idea of the precursors method, the solid state method of making LFP. This is generally what we've seen to date. It involves a lot of crystallizations. Usually the purified phosphoric acid is crystallized in the form of a TMAP. It's reacted with, iron sulfate, which is in the crystallized format as well. A precursor is made called iron phosphate. Then iron phosphate is mixed with another precursor that's made lithium phosphate. And then, you create the LFP this way. And this is now the hydrothermal method. This is the different method. As you can see, it's a lot cleaner method. It involves in situ wet materials. Generally, there are no crystallizations involved in this. So it's a great method, but it's also a method that really requires these elements all in situ. And that's what we're working on at First Phosphate, to have all in situ materials in North America to be able to give life to these more modern methods of making LFP, or to use the traditional method of making LFP. And as you can see, green power it's a big component as well, as we discussed earlier. So, where do we go from here? Like, what is it going to mean? What is the next steps? What can we look forward to? Well, when you start making these processes outside of Asia, and you've got them in North America and Europe, integration into supply chains of major EV manufacturers is very important. Leaning into just-in-time management systems, the need to be able to understand the supply chain, to understand your client downstream. And let's remember, these are very high maintenance clients downstream. Like, if you want to put together a contract with, a Tesla or a GM or a Ford, you're looking at a very long contractual process, and you're tied down to, a lengthy set of liabilities, or lengthy set of achievements that you need to make. Like, your specs need to be consistent. So, you really start getting really integrated with the manufacturer very quickly, especially in the EV sector. So that's something to really understand. This is not going to be an afterthought of the food fertilizer business. It's, let's not reach for a shiny object here, but let's really understand what we're doing and why we're doing it. And when we get into it, let's really understand what we're getting into. You're really getting into a logistics process. You're really getting into a very serious high-end and, high maintenance customer down the road. This is high technology. Okay. Now, what do we see as kind of one of the constraints to all of this? It's obviously purified phosphoric acid, right? This is a specialty product. As we know, the world of phosphate is, about 80% fertilizer, MGA, then another 10% of MGA for animal feed. Then there's just this 10% category that is, purified phosphoric acid, which is, in food. We find it in, obviously, Coca-Cola cans and other beverages. Electronics as an etching agent. We'll skip over LFP for now. We got it in industrial applications, paints. We got it in pharma, water, fire safety. But this really here is a category, LFP, that's going to blow everything out of proportion. Like, we've done some general calculations, and it seems like we're going to need 2 to 3 times the amount of PPA that is currently available in the Western world by 2030. By 2040, that, doubles or triples again. And, there's not enough capital, there's not enough time to catch up on this. So basically, this is going to be, purified phosphoric acid is going to be very much, supply constrained. We do see prices of purified phosphoric acid with respect to MGA probably decoupling, with MGA becoming, much more sought after and more expensive. So, any demand, any supply that can be created in PPA will be very welcome in the market. Now, some people say, will that compete with food? Well, it won't necessarily compete with food, because it's just competing in this industrial segment, right? The purified phosphoric acid. But, purified phosphoric acid does have some food applications as well, quite a few of them. So, here's what is happening, right? Is the growth in LFP cell demand is going to go this way. And, if you look at, North America, which we're familiar with, you look at the, amount of merchant grade phosphoric acid and purified phosphoric acid, what it's been doing since the year 2000, it's only been going down. We have, almost 40% less, but instead we're going to need to go this way and create more MGA, which then becomes PPA. So how do we do that? There's an interesting article here, and it's also on the First Phosphate website on the main page if you'd like to read it. It was written by Yves Caprara, the ex-CEO of Prayon. He talks about all these supply chain issues that are going to come about within the PPA world because of the electrification. We've done some small little demand estimates for LFP cathode active material. This is just for EVs, okay? And EVs, like we said, is only like maybe 10, 20% of the category. And we don't even have, this is just for small EVs. We don't have buses, we don't have commercial transportation in here. So you can see by 2030, we're going to need, 750,000 tons of LFP cathode active material. That is probably about, 550,000 tons of PPA at 85%. It's just for small vehicles. That's in North America. Europe is a little bit less, but now Stellantis has started to move into LFP, so it can follow the same curve as North America. So we're going to be needing a lot of PPA is what I'm trying to get to. What we're trying to do here at First Phosphate, just to end off our program here, is we're trying to bring into production a number of deposits in the igneous world that were never deposits that were not in competition with food because they didn't exist before. So we have two major projects, one here at La Colorinial, it's about 140 kilometers from the deep sea port of Saguenay. Another one here at Baie-Jean-Lamarche, which is 75 kilometers from the deep sea port. And we're also looking to implement a PPA facility here at the deep sea port of Saguenay. So that should provide out, quite a bit of PPA just destined for the LFP battery industry so that there is no competition for food. Because again, these are virgin deposits that will just be coming online. Again, just, briefly, it's going to be a massive industry here, this LFP battery industry. But when you try to onshore it into North America, the big problem is that there's a serious shortage already of phosphate in North America. Phosphate is depleting. Reserves are a capacity for fertilizer, and the sedimentary mines cannot push out enough PPA. So what we're proposing ourselves really is to, something like, the Saguenay-Lac-Saint-Jean region of Quebec, where we have this, very pure igneous rock, is to make this the LFP battery valley of North America, a full ecosystem where we can produce all the LFP that's needed for, electrification needs in North America. Europe would need to do something similar. Again, our advantage is we're in a friendly jurisdiction. We got the right type of rock, igneous and orthosite rock, and we can make a lot of PPA to be shipped, PPA and eventually LFP cathode active material to be shipped across North America. Here is how we see the ESG-driven LFP battery ecosystem for lithium iron phosphate battery developing in North America. First Phosphate plans to focus right here on extraction and beneficiation. So at the mine site, we're able to beneficiate. We're able to get ourselves up to almost 41% purity of apatite. As you know, the maximum purity of phosphate and apatite is 42%. So we get very close to theoretical maximum. That's really what we're going after, is high purity, because we know that high purity in gives high purity out as well. So in our pilot plant, we've been able to get to this level. Then in the next step is to move towards purified phosphoric acid. We have a partnership in place with Prayon, who's got the leading technology for making purified phosphoric acid, and we believe that 90% of the beneficiated rock that we prepare will be able to be converted into purified phosphoric acid, and then eventually, into LFP cathode active material at the port of Saguenay, hopefully, where we have hydro as well, which is very important. And then from there, once you've got the LFP cathode active material, the powder made, then it goes into all sorts of cells and battery packs, and can feed any type of application in North America. So this is how we see it developing. And First Phosphate really wants to focus in on here: extraction, beneficiation, getting a proper ESG-driven mine going, maybe one of the first phosphate ESG-based mines in the world, and then eventually working with partners to get to LFP cathode active material, only the strongest in the world. So just some final thoughts here. We feel that LFP will drive the new narrative on phosphate far beyond fertilizer, and perhaps even establish a new entire modus operandi for the industry. So what do we mean by that? We think it's going to bring a big ESG magnifying glass on our industry quicker than normal. So we have to be really careful, whether we're in fertilizer or in foods or an LFP battery. Our whole industry has really got to start looking at our process, our carbon footprint, because as soon as we start producing phosphate for the battery, which we already are, and it's inevitable, everybody in the battery sector is going to be picking apart at our supply chains to see where we stack up in terms of the carbon footprint, et cetera. But I don't think we need to be scared about that. I think we have to look at this as a magnificent opportunity for our industry. It's a little sliver of our industry, which was purified phosphoric acid. It's was the tail, and now it might become the tail wagging the dog. A lot of the revenues of the industry will be in there. We have to do this in a proper fashion so that it doesn't compete with food. We have to bring online new deposits that don't compete with food, like we're trying to do with the igneous rock in Quebec, and deposits that are igneous and can produce a lot of purified phosphoric acid, which is important, because if you're making it out of sedimentary rock, then you have a lot of leftover fertilizer grade that has to be used somewhere. So in using the igneous rock, it's almost a pure play on creating purified phosphoric acid for the LFP battery, and that's why we're into it. And we see this industry really, becoming an industry of sharing, one of partnerships and investments. I will let you know that, First Phosphate is open to partnerships with anybody in the world. We're also open to investment. And, if you do need to get in touch with us, you can find my information on the next page. To finalize, our prediction is that, you build as much ESG-driven PPA for LFP cathode active material as possible. It will all be uptaken. This LFP cathode active material is one of the most versatile forms of electric storage known in the world at the moment. We're very lucky to have this, in our industry. So it's something that we should really, embrace, and we should all work together, get organized as an industry to become a sharing industry, right? And to make this, a forefront of our industry. There's a lot of demand for this LFP cathode active material. We will never be able to fulfill it all. So there's enough to go around for all of us. So it's very important that we work together as an industry and come at this as as an industry in a unified fashion. So that's it. I've finished here. This is my my email address if anybody would like to email me. I do apologize I was not able to be present personally because of some family reasons, but I look forward to getting together with everybody in future at some of the next IFA events. Thank you very much.